Hello there. In this video, I want to talk a little bit about separable differential equations. These are really useful because they're some of the earliest differential equations that you might run into while studying the subject, and they can also model quite a few physical phenomena in the real world. So it's a really useful starting point when studying diff EQs. So a separable differential equation has this form: dy dx is equal to f of x times g of y. So in order to solve a differential equation of this form, what we first can imagine doing is let's go ahead and divide both sides by g of y. And if we do that, we're going to be left with 1 over g of y times dy dx. And this is going to be equal to f of x. And then from here, if we integrated both sides of this equation with respect to x, so let's go ahead and do that real quick. We're integrating both sides with respect to x. Of course, on the right-hand side, yeah, if you give me a function of x and ask me to integrate it, yeah, I can integrate that. If I look on the left-hand side here, right, and this next step, its true basis is in the chain rule, but we exploit this all the time in mathematics, right? That more or less the dx's in this integral will roughly cancel out with each other. This is a perfectly valid manipulation, and again, it's rooted within the chain rule itself, but we use it all the time in situations like u substitution and of course in this example, right? So if we're good with this step, then we're left with a really nice form where we have the integral of dy over g of y, and it's equal to integral of f of x dx, right? And from this, we're very easily able to, oh yeah, if you give me a function of y, I can integrate with respect to y, and if you give me a function of x, you can integrate with respect to x. Or in other words, we were able to separate out the x components and the y components, and then we can just integrate each side individually and get our answer. So now that we've shown this statement to be true, let me show an identical way to get over to this that is a little bit conceptually simpler, right? So if I have dy dx equals f of x times g of y, one way we can really quickly break this down is if we treat dy dx like a fraction, right? And I want to emphasize that we're just treating dy dx like a fraction in the context of separable differential equations. If we treat dy dx like a fraction, then we can multiply both sides of our equation by dx, right? And then of course we can move the g of y over to the other side. Just like so. And then we're left with the exact same form, and we can integrate both sides again in order to solve this. Okay? So we can see that if I decide to treat dy dx like a fraction, then we can get ultimately the exact same form as we did here, right? So let's go ahead and walk through a couple of examples next and go ahead and utilize separable differential equations in some physical models. So for this first example, let's go ahead and look at this barometric equation. Where does this barometric equation come from? We don't need to know, right? This is purely just a mathematical exercise to get us comfortable with differential equations. So the answer, this is a physics model that somebody had to derive and come up with, but we're just going to use it in order to help us learn about these differential equations. So we have dp dz, right? The rate of change of my pressure with respect to height is given by a bunch of constants minus mg over rt times the current pressure of wherever you're at. Okay, so that's what this differential equation is saying. And then we're also given this initial condition here on the right that our pressure at our height z equal to 0 is equal to 1 atmosphere, or 1.01 times 10 to the 5th pascals. I'll go ahead and discuss the initial condition in more detail shortly. So, let's go ahead and start by separating this differential equation out. So I can take both sides of my equation, divide by p, right? And I can also at the same time multiply my equation by dz. See, I just divided this equation by p, and I multiplied this equation by dz, and there was the result. I've successfully separated my variables out, right? On the right-hand side, I just have a bunch of constants times dz, and on the left-hand side, I just have dp divided by pressure. So this is all in terms of pressure. This is all in terms of z. Really, there's no dependence on z, it's just a bunch of constants. So let's go ahead and integrate now that we've successfully separated our variables out. What's the integral of 1 over p with respect to p? Well, that's just the natural logarithm of p. And of course, this is an indefinite integral, so this is plus some arbitrary constant c. Okay, what about this integral? So we have the integral of minus mg over rt dz, right? And so this is simply going to be equal to negative mg over rt times z, because again, this is just a big constant. And again, this is an indefinite integral, so this is also going to have some arbitrary constant, d. But of course, if we're here, if I subtract c from both sides, right, then we get a new constant on this right-hand side, which I'll just call this fancy c, right? And we're left with ln p equals minus mg over rt z plus c. And we can see from this, right, that when we perform this integrating both sides of this equation, we can choose to put our arbitrary constant c on whatever side of the equation that we want, right? And so let's go ahead and isolate p so that we have a pressure as a function of our height z. And of course, we can do this by taking e and raising each side of the equation to that power. So e to the ln of p is just going to give me p. And again, I'll note that this is now a function of z, as we can very clearly see. And this is going to be equal to e to the minus mg over rtz plus c. And let's remind ourselves for exponentials that we can write this as e to the c times e to the minus mg over rtz. And once again, e to a constant is just another constant. So again, I'm going to recategorize this constant yet again. So this is still another constant times e to the minus mg over rtz. And this is just our pressure as a function of the height. The problem is, here we have a general solution for this differential equation, because we still haven't defined what c is. C is still just an arbitrary constant. We need to specify exactly what c is. We can do this by applying our initial condition. So let's scroll up and remind ourselves that the pressure at a height of equal to 0 is specifically, because we've defined it this way, this is equal to P naught, which happens to be 1 atmosphere. Okay? So let's go ahead and plug that in. My pressure at a height that z is equal to 0 is equal to P naught, right? So let's go ahead and plug in z is equal to 0 into this equation. Then we have c times e raised to 0. Oh, and e to the 0, that's just 1. So we're left with c is equal to P naught. Awesome. So now that I've done this, I have a particular solution to my differential equation. So we have P of z is equal to P naught e to the minus mg over RTZ, where P naught is equal to 1 atmosphere, or about 1.01 times 10 to the 5th pascals. Awesome, we just solved our first separable differential equation. Not that bad at all. And again, before I head off, let me just make a note real quick that again, in contrast to this general solution up here, where we had an undefined C, this is a particular solution in which we got rid of that arbitrary constant C and now have a truly singular, well-defined function, pressure as a function of height. And with that, I'll go ahead and end this recording here. I hope you found this video helpful. Thank you so much for watching.